Okay, till the last few sessions, we have learned about the basics of Six Sigma, the define phase and the measure phase. So now we move on to the analyze phase. So in the analyze phase, based on the data we have collected for doing the process analysis and the data analysis, we are going to analyze the data, and then we are trying to find out what are the root causes for the problems. And the very important thing is that we will have to validate the root causes by using statistical tools. So the output of an analyze phase is the validated root causes. Validation means validation being done by a statistical tools. So it is not acceptable in Six Sigma methodology that root cause is validated just by doing some brainstorming session or not qualitatively. So it has to be quantitatively validated using some statistical tool. So by the end of this phase, we will be able to explain the different patterns of variations. So we will be able to identify where the variability is more, so that we will be able to identify the root cause of the problems. Then we will be able to define the inferential statistics, illustrate hypothesis testing, and then perform the different hypothesis tests for normal data and perform the different hypothesis tests for non-normal data. So this patterns of variation, this hypothesis testing, these tools will help us to identify the root causes of the problems. So coming back to what I told, what we do in the analyze phase. So we are doing two types of analysis. The first one is the process analysis, where we do the process analysis using some tools like the value stream mapping or cause and effect diagram or a lot of other tools we have learned during the measure phase. So using these tools, we are trying to do a detailed analysis of where the problems are lying. So wherever any wasteful activities are happening or wherever non-value added activities are happening, then that can be eliminated so that the process becomes very simple. And then we are also collecting the data during the measure phase. So using this data, then we will be using some sophisticated statistical tools like hypothesis testing, regression analysis, and a design of experiment. So using these experiments, then we will be able to find out the root causes of the problem, and we will be able to validate those root causes. So this hypothesis testing, again within that we are having the chi-square test, t-test and ANOVA, then regression. So using this hypothesis testing, we will be able to identify whether there are any differences between products being manufactured under different conditions. By using the regression analysis, we will be able to verify the root causes, and by using the design of experiments, we will be able to screen and compare the use and screen and identify the major impacting root causes. So in this session, we will learn about the patterns of variation. So under this, we will learn about the multivariate analysis, and then we will also discuss about the different classes of distribution, probability distribution. So multivariate charts are a way of presenting variance from a data in graphical form, helping to carry out an investigation and study patterns of variation from many possible causes on a single chart. So it graphically represents the relationship between the factors and response. Then it is used to identify possible X or families of variations, as such variation within piece or within transaction, then piece to piece or transaction to transaction variation, and over time. So this multivariate chart is used to analyze the effects of categorical inputs on continuous output. Okay. So I will just give a brief explanation about what is done in the multivariate chart. So assume that a machine is producing some parts. So there are, and then this machine is running continuously using the different materials, different operators, and different batches of powder. So in that case, what happens is, whenever the parts are produced, then within a part itself there is a possibility of some variations coming in. So we call it as a within piece or within piece transaction. And then whenever the machine is continuously producing, and then in an hour say 1,000 pieces are produced, so there may be a variation between the different individual pieces whatever are produced during the 1 hour time. So this we called as a piece to piece variation. So within piece, then piece to piece, and then time to time. So whenever this machine is running continuously, then again the operators may change, the batch of materials may change. So because of that, again variations may come. So this we call as a time to time. So whenever we want to study which is going to be the major source of variation, we'll have to first really see whether the within piece variation is more, or piece to piece variation is more, or time to time variation is more. This we need to clearly understand, because whatever the factors which are going to contribute for within piece variations are going to be different from the causes which are going to cause the piece to piece variation, which in turn are going to be different from the causes which are going to cause the time to time variation. So we need to really understand out of these three types which type is having the maximum variation, so that whenever you are going to collect the data, we will be able to focus only on collecting those data, so that we will be able to identify the major causes of variation. Suppose in a particular case the piece to piece variation is more, then we are collecting more data on time to time this thing, like different operators and different shifts and all. Then it may not be relevant. Collecting that type of data may not be relevant, because most of the variation is coming from piece to piece. So doing a multivariate chart will help you to identify out of these three variations, this within piece, piece to piece, this we call that as cyclic. So this is a positional, this is a positional variation, this is a cyclical variation, and this is a temporal. So the within piece variation we call that as a positional variation, piece to piece we call that as a cyclical variation, and the time to time we call that as a temporal variation. So out of this three variation, which is more, we will be able to see that by plotting the readings in a multivariate chart. And then once we know which type of variation is contributing more, then we can start collecting the data in order to identify the reasons for the higher variation in that particular category. So that is the purpose of doing a multivariate chart. So here is an example we have given. So here we want to study the output we are talking about is the strength. So you want to check whether the time of the processing, whether that is having the more impact, or the metal type. So there are different types of metals are there. So out of these two, which is having more impact on the strength. So then we just collect the data and then put it into the Minitab software. Then we are getting an output like this. So from here you are finding that the time is a major this thing where the variation is more. Whenever you are talking about this, so within the time we are getting within the same metal we are having the difference from 17.5 to 21.5. So that means this is actually within piece variation is more. Within piece variation is more when compared to piece to piece. So different metals, if you see the variation, the maximum variation is between say 19.5 and 22. So only 2.5 is the difference. Whenever we are comparing that, this is the maximum difference whenever we are comparing the metal types. But within the piece, like different time of sintering, we are finding that the variation is from 17.5 to 21.5, that is 4. So then we can say that the within piece, that means within a single metal type, the variation is more. Then we need to really go into deeper and then see what are the different factors which are contributing to higher variation within that particular metal type. So then we will have to accordingly collect the data, then we will be able to identify the root cause of the problem. Okay, next we move on to learning about the probability distribution. So if you remember, whenever we are covering the measure phase and we were discussing about the statistics, I was discussing you about the probability theory, which is useful for the Six Sigma projects. So now we will just see the different types of probability distributions which are going to be helpful during the analyze phase. So first we will talk about the binomial distribution and the Poisson distribution. So binomial and Poisson distribution. So any probability distribution, we can call that is a pattern. So what do you mean by pattern and why it is helpful to understand the pattern? It is because, say for example, when we were discussing about the normal distribution, and I gave the example of trying to predict the height of the Indian adults who have assembled in a particular hall, then we have seen that the height of Indian male adults shows a pattern over the last so many years, and it shows that the average height varies between 1.5 to 1.85 meters, so that we will be able to predict that even if 10,000 people are going to be assembled in a particular hall, then we should be able to see how many people will be having the height between 1.5 to 1.6, 1.6 to 1.7. This we will be able to predict using the already known knowledge we have about the normal distribution. Same way, binomial distribution is applicable in certain cases, and then it is having a certain pattern, and then using the pattern, then we will be able to predict how the samples are going to behave. Same way the Poisson distribution. So first we will talk about the binomial distribution and then about the Poisson distribution. So before going into the binomial or Poisson, we need to understand the difference between the defective and defect. So this is very important if you want to really understand what is the difference between when we have to use the binomial distribution and when you will have to use the Poisson distribution. So say for example, you are manufacturing pens, right? So suppose you are producing 100 pens, okay, 100 pens, and you are checking all these 100 pens, and then whenever you check a pen can be defective, it can be rejected if you are finding that the dimension is not okay, or the ink is not okay, or there are some cracks, or there are some chip-offs. Okay, these are the four criteria you are considering for checking whether the pen is okay or not okay. Then using these four criteria, you are checking the pens, and then you are finding that on a particular day you have produced 100 pens and you have rejected 2 pens rejected. Okay, and then why you have rejected 2 pens? Because in one pen you find 3 defects, like dimensional, ink and crack was there in one. 3 defects were there in one pen, and in another pen you had 1 defect. That means it was having a chip off. Okay, so now what is the difference between a defective and a defect? So defective means whichever is rejected because of having the defect. Even if there is going to be, it is going to be rejected even if there is going to be 1 defect in that particular pen, or even if it is going to be 6 defects in the pen, it is going to be rejected. Then we call that as a defective pens, right? So here we say that there were 2 defective pens were there. In this lot, since 2 pens got rejected, the number of defective pens were 2, right? But how many number of defects were there? In the first pen there were 3 defects were there, and in the second pen there was 1 defect. So number of defects was 4. Okay, so the main difference between the defective and defect is anything which is not conforming to the, if a particular parameter is not conforming to the specification, then we call that as a defect. We have got a specification for the dimension, and if it is not meeting that, then we call that as a defect. Then the same item has got some specification for the visible defect. It should not have any crack. If there is a crack, then there is a defect. Okay, so there is a possibility of a multiple defects in a defective product. Okay, so here in this example, the number of defective pens were 2, and the total number of defects that were found in this 100 pens were 4. I think now you are very clear between what is the difference between defective and defect. Okay. So now coming to the context of learning binomial distribution. So this binomial distribution is used for, as I had told you when I was explaining the probability theory, the probability theory is helpful when you have the knowledge about the population, but you do not know how the samples are going to behave. So in such cases, you can use the probability distribution. So that's what we are looking here. It is an application of the population knowledge to predict the sample behavior. A process is called a Bernoulli process or a binomial process when the process output has only two possible values. So whenever a process is done and the outcome, there are only two possibilities, either yes or no, or pass or fail, or defective or okay. So in this type of cases, when there are only two possible outcomes are there, then we call that as a binomial process or a Bernoulli process, and we can apply the binomial distribution for this. So here the second condition is that the probability of each outcome remains constant over time. So that means, like say for example, I just to explain the binomial distribution, I just give an example of tossing a coin. Okay, tossing a coin. So what are the possible outcomes whenever you are tossing a coin? Only there are two possibilities are there. Either you can hit a head or you can get a tail, right? So there are only two possible outcomes. So that means this is meeting the first condition. That means the process has got only two possible values. Okay. Then the second condition is that the probability of each outcome remains constant over time. So that means whenever you are tossing a coin for the first time, then what is the probability of getting a head? So the probability of hitting the head the first time is 1/2, right? There are two possible outcomes, and then the probability of hitting head is 1/2, right? Then again you are tossing the coin for the 50th time. What is the probability of, that is the probability of getting the head in first trial is 1/2. What is the probability of hitting the head when I am tossing the coin for the 50th time? Again it is going to be 1/2. It is not going to change. What is the probability of getting the head whenever I am tossing the coin for the 1000th time? Again it is going to be the same, 1/2, right? So that means the probability is not going to change. It is going to be constant over time. Then we call that, we can apply the binomial distribution. So this particular thing meets the second condition. The third one is outputs are statistically independent. So that means here the output is always 1/2. It is not dependent upon, like the outcome of the first trial does not have any impact on the outcome of the 50th trial, or does not have any impact on the outcome of the 1000th trial. So each and every trial is an independent trial. So again this is meeting the third condition, right? So if these three conditions are met for those processes, we can apply the binomial distribution. Okay. So the mean of a binomial distribution is equal to NP, and standard deviation is equal to NP and to 1 minus P. And as I told you, binomial distribution is measured on, is applicable for defectives and are not on defects. It is more suitable when n, that is the sample size, is less than 30 and the probability of that event happening is 0.1. Okay. So why and when we can use this? Okay, because you need to know what is the application of using the binomial distribution. Say for example, based on your past history, you find that on an average, say suppose you are doing inspection of some chapters, right? You are doing the content editing at the final stage, and then every day you are checking, say around 100 files, right? So every day you are checking some files and then collecting the data, and then you are finding that the average whenever you are checking 100 files, maybe 5 files are defective. 5 files are defective. So that means average defective files is 5% based on the last 1 year. 5% based on last 1 year data. So this is what you know about this is what the knowledge of population knowledge you have. That means based on the past data, 5% of the files are found to be defective. So now today you have received 50 files for checking, right? 50 files for checking. So now you want to see out of these 50 files, what is the probability of getting 0 defect, means no files being defective. What is the probability of getting that. What is the probability of getting one file as defective? What is the probability of getting two files as defective? So this you will be able to predict using the information whatever you are having and using the binomial properties of binomial distribution. I think the application when we are going to apply this binomial distribution is very clear to you. So here you have the formula. So the PR, as I told you, say for example the n is a sample size. The example I gave you, today you have received 50 files. So n is a 50 here. And the number of successes desired. So as I told you, if you want to file, out of these 50 files, you want to calculate what is the probability of getting 0 file defective. What is the probability of getting 1 file defective. So the 0, 1 and all. So these are all the R. And the probability of success is the what we already know that 5% of the files is based on the past history. The P was the probability of getting success was defective file was 5%, right? So using this data and using this formula, you will be able to predict what is the probability of getting the 0 defective file and the probability of getting 1 defective file, etc. So this is what we learn about the binomial distribution. Okay. So the next one is the Poisson distribution. So this is also a probability distribution for discrete data or the attribute data. So again, this is also an application of knowledge to predict the sample behavior. So unlike binomial distribution that deals with the binary discrete data where you had only the yes or no type, the Poisson distribution deals with integers. Okay. So whenever we talk about the integers, again if you see, it can be used for the number of prediction for the number of defects. So you can see that the binomial distribution you are using when we are just doing the prediction on the defectives, and the Poisson distribution you will use for whenever you want to predict what is going to be the number of defects. Okay. So this distribution is generally used for describing the probability distribution of an event that tends to occur at predictable intervals of time. Okay. It is suitable for analyzing situations where the number of tails is very large and the probability of success in each tail is very small. Okay. So I will just tell you an example where you can apply this particular distribution, then it will be easy for you. So for example, you know about the insurance companies, right? Insurance companies. So how does an insurance company work? What they do is they are covering the risk for any accident. So for example, now insurance company is focusing on the insuring the people who are traveling by airplane, right? So where they will be spending more money apart from their administrative and other employee expenses and all, where the bulk of the money is going to go out. So that is for paying for the affected people, right? So the outgo is paying for affected people. Whenever there is an accident, whenever the plane crashes, then they will have to give the compensation, right? Paying for compensation. Okay. So that is the outflow. So where the money is going to come from, where the inflow is going to be there, the inflow is going to be from the premium, right? So who is going to pay the insurance premium? So all the passengers who are going to travel by air, they will be paying some premium, right? Say for example, every day that insurance company is giving coverage for around say 1 lakh people. 1 lakh people on an average are traveling every month, okay, using this company's insurance. So they are going to collect the premium from all the 1 lakh passengers. But if a plane crashes, then only maybe 100 or 150 people are going to be affected. And then the company has to pay a very large amount as a compensation if an accident happens, right? So now if the company wants to fix the premium, how much it will charge as a premium for all the passengers, so that in case the accidents happen, then they will be able to pay compensation to the victims, right? So for that, one of the important thing what they need to do is they need to predict the number of accidents, air crashes that can happen in, say, in a year. So they will have to know that, okay, in this particular year, what is the probability of an air crash that is going to, how many number of air crash is going to happen. Okay, in order to predict that, what the information they are already having is, they know that over the last say 20 years, the average number of plane crashes, say it is equal to 5. So they know that over the last so many years, the average number of plane crashes per year is 5. So using this information, they have to predict what is the predicted number of accidents this year. So based on that, they will be able to calculate what is going to be the likely compensation they will have to give, and then once they arrive at this number, then they will be able to calculate what is the premium they will have to collect from the passengers. So the Poisson distribution is used for, here we are considering that accident as a defect. So here we are trying to predict the number of defects which is going to happen using our knowledge of the past. Okay, so we already have the population knowledge based on the past data, and then we want to predict what is going to happen in future, how many number of defects are going to be generated. So we want to predict that. So for predicting the number of defects in future, then we use this Poisson distribution. So for using this, for making this prediction, then we use this formula. Then using this formula, we will be able to know, so here this lambda. So here the lambda is the mean number of occurrences during year. As I told you, I gave you the example that the average number of accidents that has happened over the last few years, average number of accidents per year is 5. So that is lambda. And then you want to predict what is going to be the probability of having 0 accident, what is the probability of having 1 accident, and what is the probability of having 2 accidents. Okay, so once you have this information, and then you just substitute these numbers in this formula, then you will have the probability values. Once you have the probability values, then you will be able to calculate the number of accidents that is going to happen. Okay, so we have clearly, this is just an idea for you to see what are the different types of probability distributions we can use. So binomial distribution for defectives and the Poisson distribution for the defects. Then we also have other probability distributions like chi-square distribution. So this is mainly used for hypothesis testing. And this will is helpful to find whether there is a relationship between variables are there. To check whether there is when we have two sets of data, for these two sets of data, whether there is a relationship is there or not. Say for example, these two sets of data I have is the amount of rain on a particular day, and this is the number of umbrellas sold. So I want to check whether there is a relationship between the amount of rain that has happened on a particular day and the number of umbrellas that has been sold. So I collect this data, and then I just put it in this using this chi-square distribution. I will be able to see whether there is a relationship between these two or not. So for doing this, we use the chi-square distribution. Next one is about, we are going to talk about the T distribution. So these T distributions will help you to identify whether there is a relationship between two means. We are comparing the means of two different populations, means of different populations, and we want to check whether there is a significant difference. So when we want to check, say for example, there are two suppliers are there, right? Supplier A
and supplier B. And then you want to check whether there is really you are just measuring these two people are supplying the steel material to you, and then you are just seeing this hardness of the steel. Hardness of steel is a parameter by which you can check the property of the steel. So now you are having the data on the hardness of the different lots supplied by supplier A, and the hardness of the lots supplied by supplier B. And now once you have the data, you want to see whether there is a significant difference between the hardness of the supplier A and B, because you know if the hardness is more, then that is good for your process. So then in order to check whether there is a significant difference between the hardness of say lots supplied by A and lots supplied by B, whether there is a significant difference is there or not, you can just check that by using the T distribution and doing the hypothesis testing. So all these distributions, chi-square distribution, T distribution and F distribution, these are all used during the hypothesis testing, but this will be applicable for different circumstances. So chi-square test is used for checking whether there is a relationship between two sets of data. T distribution is useful if you want to find out whether there is a significant difference between the means of two different lots, and F distribution is used to find if there is going to be a significant difference in the variation, whether the standard deviations or variances, there is a significant difference. Okay. So regarding this hypothesis testing, what we are doing, how we are doing and all, we will just see whenever we are doing that session on hypothesis testing. So now in this session you learnt about the patterns of variation, that is the multivariate analysis, and we also saw the different probability distributions like binomial, Poisson, chi-square, F distribution and T distributions, and then what are the applications of those. So doing the multivariate analysis and the probability distributions will help you to identify what are the possible reasons for variances. Okay, let's start with a session on the inferential statistics. So at the end of this session, you will be able to understand how to interpret the inferences. That is what we will learn more about the inferential statistics. We will also see what are the different sampling techniques, and we will also learn about the sampling size, and we will also discuss about the central limit theorem. So what is central limit theorem and how this can be applied. So when we were discussing about the basic statistics in the measure module, then we also saw the inferential statistics as one of the branches of statistics which will be helpful to us. So there we also saw about the basics of this inferential statistics. Okay, so to recap whatever we discussed about the inferential statistics. So in inferential statistics, here it is a set of methods used to draw conclusions and inferences about characteristics of populations based on samples, data from samples. So that means in inferential statistics, what we know is we have the data collected from the sample, but we do not know about the population. So that means, say for example, one of the classical example of inferential statistics, as I had explained, was the opinion polls or the exit polls. So in opinion polls or exit polls, what we are trying to do, say for example, there was a by-election, right? In a by-election, there was a by-election, and then in this by-election, some 4 contestants, A, B, C, D, or these 4 contestants are contesting. So now a particular TV channel, they wanted to just predict out of these four contestants who is going to win. Assume that in this particular consistency there are 15 lakh voters are there. So 15 lakh voters are there. So if these 15 lakh voters are there and the TV channel wants to predict out of these four contestants who is going to win, is it possible for the TV channel to contact all the 15 lakh voters and then get their voting preference and then come out with the results about the opinion polls? No, it is not possible. Then it is as good as conducting the election itself. So in that case, what the TV channel will do, then out of these 15 lakh voters, then they will randomly pick up maybe a sample of say 5,000 people. So the 5,000 as the sample size. And then they will contact these 5,000 people and then they will ask their voting preference, whether they are going to vote for A or B or C or D. And then they will just get the results based on the preference they got from the 5,000 people. And then they may say that out of these 5,000 people they have contacted, then maybe 3,000 people may they say that they are preferring A, B around 1,500 people are preferring, C 400 people are preferring, D only 100. So in this case, then the TV channel may say that they may predict that the A may win the election. So here what we are trying to do, here the population is 15 lakhs, right? This is the population size. And what is the sample? 5,000. So here we have the results or the data from the samples, right? We know everything about the sample because we have collected the data from the samples, and then we know everything about the sample. What is the voting preference of the people from the sample side? So once we know the result, so we are trying to predict the population's behavior based on the samples. Okay, so this is what we call it as a inferential statistics. So whenever we know everything about the sample but we do not know about the population, using the data collected from the sample, we try to predict the behavior of the population. We call that as a inferential statistics. Okay, so this particular inferential statistics is very much helpful, not only for the opinion polls or exit polls, but also related to a lot of process problems, right? So whenever we have some process problems, so I will just give an example when this type of inferential statistics is helpful. And one of the very important statistical tool which is used in inferential statistics, we call that as hypothesis testing. So this hypothesis testing is a sort of a inferential statistic, and then using this hypothesis testing we will be able to solve a lot of process problems. So in the coming sessions on hypothesis testing, the hypothesis testing on normal data, then hypothesis testing on non-normal data. So in these three sessions, then we will be talking in detail about this inferential statistics. So here in this particular session, we will just know what is the inferential statistics and then how we are going to do that. So that basic knowledge we have got it from this session. Okay. So based on the last slide, we knew that in order to do an inferential statistics, we'll have to draw samples. So in this slides, we will talk about what are the different sampling techniques and what are their uses. So sampling is the process of selecting a small number of elements from a larger defined target group of elements. Okay. So sampling is the process of selecting a small number of elements. So this small number of elements is the samples. And the from a larger defined target group of element, that is a population. So in the example I gave you for the last slide, see, whenever we are having a by-election and there are going to be 15 lakh voters are there, then these 15 lakh voters we call that as a population. Okay, and then in order to know, predict who is going to win as a part of the opinion poll or the exit poll, then out of these 15 lakh people we are going to select 5,000 people. So these 5,000 people we call that as a samples. Okay, so when we are have to do the sampling, okay, in which situations we will have to do the sampling. Okay, so we will do the sampling when the process involves destructive testing. Example, taste test, car crash test, etc. So for example, we have to now we have produced around 10,000 parts, and then we have to check whether these 10,000 parts are okay or not. So, but if you want to check it, then the testing needs it's a destructive testing. That means only if the sample is destroyed, then only we will know whether the sample is this okay or not okay. So we cannot do the test on all the entire 10,000 parts. So then what we will do, out of these 10,000 we will randomly pick maybe 5 parts or 10 parts, because we know that after the sampling is done, the sample cannot be used, it has to be destroyed for doing the testing. Then we will be selecting only 5 or 10 number samples. Okay, so we use the sampling when the testing process is a destructive testing, or whenever there is a constraints of time and cost. So for example, you just see a company which is producing some automobile components, right? Automobile components. So then maybe a particular component, they may produce 100,000 parts every day. So if they are producing 100,000 parts every day, is it possible for that company to do a 100% checking on all the 100,000 parts? No, that is not possible, right? So in that case, what they will do, they will just have a sampling plan by which they will say that if 100,000 parts are produced every day, out of these 100,000 parts, maybe they will select 1,000 parts, and then they will test all the parameters on these 100,000 parts, and then they will have some planning. Out of these 100,000 parts, if the failure is less than 10 parts, then they will accept it. If the failure is more than 10 parts, they will reject the entire 100,000 parts. So this we call that as a sampling plan. Okay, we have a lot of we have some universal sampling plan, approved sampling plans are there. Then they will follow as per the plans which is universally accepted or which is accepted by the customer, and then they will test their parts as per the sampling plan, and then they will accept or reject the entire product will not based on the sampling. And then the next the other way when the sampling is done is when the population cannot be easily captured. So for example, take a case when the project is for collecting the data from the drug addicts. Okay, so say for example, the project is to do a survey on drug addicts, some habits of drug addicts. So is it possible for the person who is doing the project to have a knowledge of all the drug addicts who are located in a particular city? Maybe they don't have the information. So in that case, they will just go by whatever the people they know about the known drug addicts, maybe 5 people or 10 people, whom the project leader will know that, okay, these are the drug addicts. Then he will go there and then contact that person, and these people will be collected as a sample. So we may not even be knowing who are all going to be the drug addicts in the entire city, whether they are 500 people or 1,000 people, we do not know. But only these 5 or 10 people as a known drug addicts only he will contact, and then he will get the information from them. So the sampling is done whenever the population cannot be easily captured. So we have clearly understood now when the sampling is done, in which situations, whenever the testing is a destructive testing, whenever there is a time and cost for doing the testing, or whenever the entire population cannot be captured. Sampling is not done when the events or on the products are unique and cannot be replicable. So for example, a company is making unique paintings, okay, unique paintings based on the customer requirement. Okay, so in that case we cannot do a sampling because the requirement maybe is there only for one painting, and then we cannot do any random sampling. So in that case we will have to do a 100% checking. Okay, so when the products or events are unique, then we cannot, and not replicable, then we cannot do the sampling. So now we will just learn about the different sampling techniques that are used. So the first one is the probability sampling, and the second one is the no probability sampling. Okay, these are the two different types of sampling, the probability sampling and no probability sampling. So what is the probability sampling? Whenever a sampling is done based on some logic, then we call that as a probability sampling. Okay, and whenever we do not have any logic, then we call that as a no probability sampling. Okay, so under this probability sampling we have four types: the simple random sampling, stratified random sampling, systematic sampling, and cluster sampling. Under the no probability sampling we have four sampling types: the convenience sampling, judgment sampling, quota sampling, and snowball sampling. So we will now have a look at each and every one of these sampling techniques. So in the probability sampling, we had the first one is the simple random sampling. So simple random sampling is a method of sampling in which every unit has got equal chance of being selected. Say the example I gave you just now, say a company is producing 100,000 automobile components every day, and the sampling plan says that they will have to take 1,000 samples to test the lot whether it is okay or not okay. Then in that case they just put all the 100,000 parts in one place, and then they will just randomly pick 1,000 parts out of this. So each and every one of those 100,000 parts is having the probability of getting selected as a sample. Then we call that as a simple random planning. Okay. The second one is the stratified random sampling. So in stratified random sampling, it is a method of sampling in which a stratum of groups are created and then units are picked randomly. So for example, a company is manufacturing pens, and then every day around 1,000 numbers of black colored pens are produced, 1,000 numbers of red colored pens are produced, 1,000 numbers of green colored pens are produced, and 1,000 numbers of so blue, black, red and green, 1,000 numbers each are produced. So 4,000 numbers is the output on a particular day. Then how they will do the checking? Then what they will do is they will first, whatever has been produced, they will first set out according to the color, and then from each color then they will pick up samples, right? Say suppose now out of these 4,000 numbers they will have to select 100 numbers as samples. Then they will select 25 numbers from red, 25 from green, 25 from black, and 25 from blue. So this is, we call it as a stratified random sampling. First, whatever the total population is there, first we will divide them into groups, and then from each group then random samples will be picked. So this is what we call it as a stratified random sampling. The next one in the probability sampling is the systematic sampling. So systematic sampling is a method of sampling in which every nth unit is selected from the population. Say for example, you assume that a process is the output of the process is coming in a conveyor, right? So then there is the sampling plan says that every 50th part will be selected as a sample. So then either there should be an automatic mechanism, or there can be a person who is standing there in the conveyor who then selects exactly the 50th part. So this type of sampling we call that as a systematic sampling. That is every nth unit is selected from the sample as sample. And the last one is the cluster sampling. Okay. So the cluster sampling is a method of sampling in which the clusters are sampled every tth time. So that means you assume that in a machine we are producing continuously the parts. So your sampling plan says that every hour you select, suppose every hour 1000 numbers are produced. So your sampling plan says that every hour out of these 1000 numbers, 5 numbers are selected as samples. So this is what we call it as a cluster sampling. That means every tth time, every hour or every shift or every day, so many numbers of samples to be collected. If that is specified, we call that as cluster sampling. So in probability sampling, we have 4 types: simple random sampling, stratified random sampling, systematic sampling, and cluster sampling. So then the other group is the non-probability sampling. So in non-probability sampling, we have 4 techniques. The first one is the convenience sampling, judgment sampling, quota sampling, and snowball sampling. So first we start with the snowball sampling. It is also called as a chain sampling or the chain referral sampling or referral sampling. So here, what is this technique is, say as I was telling you, suppose a particular scientist is doing a project on the behavior of the drug addicts. Okay. So in order to get the feedback, then he needs some sample drug addicts to be selected for getting some feedback. Then in that case, suppose if he is doing the project at the New York City in US. So in that case, he may not be exactly knowing how many number of drug addicts are there in New York, whether it is 100 or 1000 or 10,000 or 1 lakh, he doesn't know. And then who are all going to be these drug addicts, he does not know. So in that case, what he will do? Then he knows only some 3 or 4 people, his known people from his own friend circle or from the relative circles. So then he will first go there and then talk to them, and then whatever the survey needs to be conducted, he will do it with that people. And then he will say that, okay, once these people are happy that, okay, this survey is useful, then they will refer their friends who are, because you know that these people, they have got their own circles, right? Then these people will say that, okay, now you can contact these people for more information. So like that, this will just expand like a spiral. So this is what we call it as a snowball sampling or a chain sampling or a chain referral sampling. The second one is a judgment sampling or purposive sampling. So here, the person who wants to do the select the sample, he will apply his judgment, okay, for selecting the samples. So for example, a researcher wants to do research on a new design of a aeroplane engine. Then he will say that he wants some information to be there. So for that, he feels that he will just contact only the people who are trained as aeronautical engineers. So here he is using the judgment, saying that only these people will be able to can be collected as a sample. So in that case, we call that as a judgmental sampling, where the person who wants to take the sample uses his judgment for the sampling. The third one is the convenience sampling or a accidental sampling. So here, the person who wants to select the sample takes the sample as per the convenience. For example, if some survey needs to be conducted, then instead of doing the about the surveys regarding about the buying behavior, so if the sample is being taken only from one shopping mall, then because that shopping mall is nearer to the place of work of a particular the person who is taking the sample, we call that as a convenience sampling, because he just takes the sample based on his convenience. The last one is the quota sampling. So the quota sampling is similar to the stratified random sampling, but the only difference is that after the stratification, in stratified random sampling, random samples are picked, whereas in quota sampling, after the stratification, judgment sampling is used for taking the final samples. Okay. Then we just learn about how to calculate the sample size. Okay. So here again the calculation of sample size will be based on the data type, whether the data is a continuous data or discrete data. And then if there is a continuous data, then the sample size n, so n is a sample size, this is a sample size. So this sample size is equal to 1.96 into sigma divided by delta whole square, where the sigma is a standard deviation of the population and the delta is the precision or the level of uncertainty estimate that you are willing to accept. So you know that whenever, say for example, if my population size is 1000, okay, and I am doing the testing on all the 1000 pieces, and this is the total population, and I am doing the testing on all the 1000 pieces, and then I am rejecting 10 pieces as rejections, then I am 100% confident. 100% I am confident that the rejection is only 10%, 10 pieces, right? But suppose out of the 1000 pieces, I take only 50 pieces as sample. 50 pieces sample. And then I just say that based on these samples, I predict that out of these 50 pieces, I get 1 piece as rejection. And then I predict that the total lot is going to have 50 samples is 1 pieces. So that means that the rejection is going to be 2%. So that means 2% of the 1000 is 20 pieces. I predict that the total rejection is going to be 20 pieces. Then since I am not doing the testing on the 100% of the population, then I am not 100% confident. So maybe I am only 95% confident or only 90% confident. So here whatever we are dealing delta is the precision or the level of uncertainty what I am willing to accept. Say suppose I may be saying that I am willing to accept 5% uncertainty. Okay, in that case delta is 0.05. If I say that I can accept as 10% uncertainty or a error in my judgment, then I can say delta is 0.1. So that is dependent upon the person who is taking the samples. Then the sample size formula for discrete data, that is equal to n is equal to 1.96 divided by delta whole square into p into 1 minus p, where p is the proportional defective that we are trying to estimate.
Whenever we are drawing the samples from the population in order to do an inferential statistics, so there is always a possibility of sampling errors. So the sampling errors can come because of two reasons. The first reason is the bias in sampling, and the second problem can happen because of the sample size. So the bias in sampling can come because if the sample is not representative of the population, and then we are not selecting the samples judiciously, then whatever the error we are getting, we call that as a error due to the bias in sampling. So whenever you are sampling, we have to ensure that whatever the assumption we are making, whatever the type of sampling we are doing, each and every type of sampling has got some assumptions. So those assumptions have to be strictly met so that we reduce the errors due to bias in sampling. And the second reason for the sampling error is because of the sample size. So the error arising from the drawing inference on the basis of observation of a part or a sample is termed as sampling error. So the sampling error decreases with increase in sample size. So as you are going to draw more and more number of samples, then the errors will come down. So if you see this graph, then as the sample size is increasing, then the sampling error is coming down. So if you are really seeing the curve, what happens is normally increase in sample size does not result in substantial reduction of error after some time. So for example, if you see at this point of time, so till this point of time, there is a substantial reduction in the sampling error when the sample size increases. But beyond this point, increasing the sample size is not reducing the errors so much. So then this is the optimum sample size which should be selected for making the inferences. So the optimum sample size is to be worked out based on this behavior, and then also taking into account what is the required precision and what is the cost we can afford. So we'll have to judiciously select the sample size so that we will be able to accommodate the precision and accuracy of our measurement. At the same time, the cost is also within control. So we'll have to select this in such a way that both the accuracy of measurement is also maintained as well as the cost is also kept in check. Okay, now we learn about one of the very important theorem which is very helpful for the analyze phase in the Six Sigma project. So that is what we call that as a central limit theorem, CLT. So the central limit theorem tells us that the sampling distribution of the sample mean is normally distributed regardless of the distribution of the underlying random sample. In fact, the CLT applies regardless of whether the distribution of the xi is discrete, for example Poisson or binomial, or continuous, for example exponential or chi-square. So the distribution of average values of sample or the multiple x bars drawn from that universe will tend towards a normal distribution as the sample size grows without bound with mean mu and standard deviation mu sigma by square root of n. So if I try to explain here, say for example you assume that this is the parent distribution. So I will just explain how this central limit theorem works for the normal distribution. Then we will just see how it works for the other distribution. So first we start with the normal distribution. So assume that this is actually the parent population, so for which the mean is mu and the mean is mu and standard deviation is sigma. So this assume that we do not know what is the population mean and population sigma. So we are trying to take the samples, and then from the samples we tend to predict what is going to be the mu and sigma for the entire population. So whenever now in order to find that say mean and sigma of the population, what we can do is we can just randomly pick up some small samples and then try to find out what is the mean and sigma. Say for example, just for easier understanding, I am assuming that overall, say for example, now the total population is having say total 2 lakh numbers. So this is the total population size, and then for this population, this is the population is having some 2 lakh parts, 200,000 parts. So for this mu we do not know and sigma we do not know. Then in order to find that, what we can do is we can just draw some samples. Say I just draw first sample, that is sample 1. I am just taking 50 numbers. Randomly I am just taking 50 numbers, and then calculate is x bar, or the average and the small s. So x bar 1 and s1. So this is the mean, is the average of the 50 numbers of samples, and this is the standard deviation of the another 50 numbers. Then I take another second sample. Again randomly out of this 200,000 I am just taking the 50 numbers. And then let it be x2 bar and then s2 bar, s2. So like that I just assume that I am just drawing 100 samples, say s100. Again I am drawing 50 numbers. Then it is x3, x100, x bar 100 and s100. So since these are all small samples, I will be able to calculate both the average as well as the standard deviation. So now what the central limit theorem says is that if I want to estimate what is going to be the mean of this particular population, then this mean will be equal to the mean of all the individual means of the samples. So that means mu is equal to the average of x bar 1, x bar 2 up to x bar 100. So if I calculate the mean of all the means of this individual samples, then that will be equal to the population mean, and then the standard deviation of the population will be equal to the sigma into root n. So this is the population, and this is actually the standard deviation. So the sigma of the population will be equal to root n into sigma of the samples. So if you start with the normal distribution, and then we find that whenever you are increasing the sample size, so instead of now taking 50 samples, if I take only 2 samples every time, if I take only 2 samples every time, then the mean is not going to change. So if I calculate the average of all the individual means, again that will be equal to the population of the mean, and the standard deviation will be equal to it will reduce to the extent of root of n. And suppose if I go on increasing the sample size for the normal distribution, if the sample size is more, then you can find that sigma for the population mean is coming less, and then we call that as a sigma by root n. So mean is equal to the average of all the sampling means, and the sigma is equal to sigma by root n. So this is applicable whenever we are having the normal distribution. So if the population is not normal also, then only the central limit theorem says that even if the original population is not a normally distributed population, and then it can be either a attribute distribution, or it may be a continuous distribution. It may be a Poisson distribution, it may be a binomial distribution, it may be a exponential distribution. So parent distribution may be anything, but as you go on increasing the sample size, then after whenever we are reaching the sample size somewhere around 30, then everything becomes more or less like a normal distribution. So this will be helpful. So for example, whenever you are measuring the handling time of any calls, then the handling time of any call is not a normally distribution. It always follows a exponential distribution. So if you want to really do some improvement on the call time for a particular, say for example, one telecom call center is there. So there you are finding that the people are spending more time for attending to calls. So you want to reduce the time taken for attending to individual calls. So if you want to measure this particular unit in terms of call time, then this will follow a exponential curve, and then it is very difficult for you to make any predictions. But using this central limit theorem, if you are calculating the average calls which are handled during every hour, say for example average call per hour, so means first hour we are handling 7, the second hour we are handling 5 calls, like that. So normally we are measuring the efficiency of the call center operators in average calls being handled. So once we are taking that average, then if the sample size is more than 30, then it will behave like a normal distribution, and whatever the statistical tools which we can apply for the normal distribution can be used for this population also. That means when we are collecting the data on call time, then since it is exponential, we will not be able to use any tools which are using the normal distribution. But once if you are taking the average handling time, then using the central limit theorem, then we will be able to, and if the sample size is more than 30, then we will be able to use the normal distribution properties for predicting the samples here. So that is the advantage of using the central limit theorem. So if a normal random variable x has mean mu and finite variation sigma square, as n increases, x approaches a normal distribution, with mu and the variance sigma x square, where sigma x square is equal to sigma square by n, where n is the number of observations on which the mean is based. So the central limit theorem states the sample means xi will be more normally distributed around mu than individual readings x1 bar. The spread in sample mean x1 is less than xj, with the standard deviation of xi equal to the standard deviation of the populations divided by the square root of the sample size. So again, as I told you, even if you are starting with any non-normal populations, then if the data is sufficiently large, so we are talking about a sample size of more than 30, then the distribution of x bars will approach a normal distribution with mu x bar is equal to mu xi. So this mu xi is the population mean, and sigma xi is the population standard deviation, and mu x bar is the average of all samples, and sigma x bar is the standard deviation of the samples. So using this formula, then even if the parent population is non-normal or categorical or binomial or any attribute data, we will be able to use the properties of normal distribution using the central limit theorem. So in these sessions, you learned about the understanding the inferences, the sampling techniques and their uses, and the central limit theorem. Okay, now in this session, we would like to cover more about the hypothesis testing. So by the end of the session, you will be able to define the general concepts and goals of hypothesis testing, explain significance level, that is the practical versus statistical p-value, discuss alpha and beta risk, and identify the different types of hypothesis tests. So hypothesis testing is a powerful statistical tool used to validate the root causes for the problem. Doing a hypothesis test is just like conducting a trial in court of law. We assume that there is no change, that is, the convict is innocent in the outcome of a process if the input is changed. If you want to prove that there is a change in the outcome of the process because of the change in the input, we need to collect the data and prove with evidence that there is a change. If it is proved that the change in input has caused a significant change in the output, then this input is validated as one of the significant X. So hypothesis testing is a very powerful statistical tool used to validate the root causes for the problem. So we have already seen that in the analyze phase, the main outcome is the validated root causes. So the validation is done statistically. So we cannot just do a brainstorming session and come out with a list of potential causes. That is not acceptable as per the Six Sigma methodology. Whatever we are identifying as a potential root cause of the problem has to be statistically validated, and hypothesis testing is one of the most important tests which is done in order to validate the root causes. So how do we do the hypothesis testing? So doing a hypothesis testing is just like conducting a trial in the court of law. So for example, one of the person comes and tells the police saying that okay, a particular person has stolen his money. Okay, then the police catches hold of that particular person and then maybe puts him in the thief. So can the police immediately assume and conclude that person who has been arrested is a thief? No, because just by somebody saying that okay, he has stolen his goods, we cannot give any capital punishment to that particular person. So what happens then? The person who is accusing that thief about the thief, he has to now prove in the court of law with evidences saying that yes, on that particular day, such and such place,
this thief has this theft has taken place, and these are the people who have witnessed that, and with evidence he has to prove in the court of law that the thief has really stolen his money. Then only the court will conclude based on the evidences, and then the court will convict him or convict the particular thief. Similar way, in hypothesis testing, what we do is we assume that there are no changes in the output when some input parameter is changed. That means no changes. So if we really want to prove that yes, because of a change in input there is a change in the output, then we have to collect a lot of data, and with the data we have to prove that yes, because of the change in the input, the change in output has been, significant change in output has taken place. So if it is statistically proved, then we can validate that particular input is a root cause of the problem, and that will be validated as a root cause. So this is what is happening in the hypothesis testing. So a hypothesis is a statement about a population parameter derived from one or more populations. So hypothesis testing is a statistical analysis method wherein a hypothesis is stated, sample data are collected, and a decision is made based on the sample data and the related probability value. So I will just give you an example of what is being done, how the hypothesis testing is done in a very nutshell, so that it is easy for you to understand. Say for example, you assume that there are two suppliers, A and B, who are supplying the raw material to you, and then you are using this raw material from both the sources, and then you are using it in the process. But there is a suspicion that because of the change in the raw material, maybe your yield is getting affected. So you are thinking that the raw material change has got an impact on the yield of the particular product. But until it is proven with data, we cannot effectively conclude that raw material change is one of the critical X factor. So what we need to do, say suppose if you are processing 10 different batches with 10 batches with A and 10 batches with B, and you just collect the data on the, say suppose 1, 2, 3 up to 10 batches, you just collect what are the yield figures. Okay. Same way for B also, you collect the data. Then what happens is, say for example, if you are trying to plot this as a normal distribution graph, say suppose now for A the yield the plot is coming like this. This is for A, and assume that this mean is 92%, and for B, so this is for A and this is for B, the yield is coming to be 94%. So we are still not sure whether there is a significant difference in yield, because there is a very small difference between 92 and 94. So we do not know whether that was this difference is because of the chance variation, or whether there is a significant difference between A and B. So we can conclude that the raw material has got a very great impact on the yield only if we get a distribution like this. Say for example, if you are getting a distribution like this, okay, so this is A, suppose this is 70% and this is B, and then we are getting this as 95%, and then we see that there is no common point between for A and B. So A is distinctly different from B. So this is clearly an indication that the raw material, supplier, the supplier of the raw material has got an impact on the yield, right? So in hypothesis testing, what we are trying to find, we are trying to find out the probability of finding a common point between these two populations. So here if you see the point I have noted here, this is actually common to both A and B population, right? So we are not very sure whether there is a significant difference. But if you see here, the point I have noted here, this P, this is actually, it is neither in A neither in B. So this actually, we can say that it is both A and B are distinctly different. So there is a significant difference between A and B. So the hypothesis testing here in this case, we are just comparing the means. We are just comparing the means. whether the means are equal or means are significantly different. Same way, using the hypothesis testing, we can also see whether there is a difference between the variabilities or the ratios. So different type of parameters also we can check whether there is a significant difference. So hypothesis testing helps you to determine if one population of item is statistically different from other items. So if you are getting the p-value like this, if you are getting a distribution like this, then we can conclude that both A and B are statistically different from each other. So what we do is, in the hypothesis testing, what we do is we first state the null hypothesis. So for the example I gave you, the null, say again we are again referring to the same example, supplier A and B, the yield with A and yield with B. Okay. So we are trying to find whether there is a difference in the mean yield of because of the two different raw materials. Okay. So the null hypothesis is the hypothesis to be tested. This is a statement of what is to be disproved. That means null hypothesis is always maintains a status quo. That means null hypothesis will always assume that there is no change. So null hypothesis will assume that because of change in the raw material, there is no change in the yield. So HO means mu A is equal to mu B. That means there is no change in the mean yield of A and mean yield of B. So that is what we call as a null hypothesis. So alternate hypothesis is the one accepted if the null hypothesis is rejected. This is a statement of what needs to be proved, because now we want to check whether there is a change in the yield because of the raw material change. So what is in our mind is that we want to prove that yes, there is really a change in the yield because of the raw material. So mu A is what we want to prove, that is mu A is not equal to mu B. That means the average yield of A is not equal to the average yield of B. So whenever you are formulating the null hypothesis and alternate hypothesis, we will have to ensure that between these two options 100% of the probability of occurrence has to be covered. So when I say that, again, if you in this case with evidence, if you are proving either null hypothesis is true or alternate hypothesis is true, these are the only two possibilities. There is no other possibility of anything different decision coming. So whenever you are going to collect the data and apply this hypothesis testing, and either we prove the hypothesis, null hypothesis, so that we conclude that there is no change in the mean yield, or we prove that alternate hypothesis is true, so that there is a change in the yield. Okay, so between this null hypothesis and alternate hypothesis, we have to come to a firm conclusion. Okay. So the hypothesis will focus on the parameters such as, so either we can do the hypothesis testing on the mean or the standard deviation or variance or proportions or mean. So there are many types of hypothesis testings are available, and the type of test which test you will have to do will be based on the type of data, whether it is a discrete data or continuous data. So let us first take the step-by-step approach for doing a hypothesis testing. So first specify the null hypothesis and alternate hypothesis. So null hypothesis, the hypothesis you are trying to challenge or you are trying to disprove, and the alternate hypothesis is the hypothesis that you have in mind or you want to prove. Okay. Then setting the alpha level. So alpha level means, since we are talking about this raw material A and B, and then we want to we want to predict how these raw materials A and B are going to behave in the future. So for this again we are doing the testing on 10 sample lots. So whenever we want to predict the results based on the 10 samples, we cannot with 100% confident, we cannot say that whatever the decision or the conclusion we are getting is right, because it is only a prediction. So there has to be some confidence level. We are not 100% confident. Maybe we are only 95% confident or something like that. So the setting the alpha level is what is the error in what is the risk we are taking of taking a wrong decision. So normally the alpha is set as say 1% or 5%. That means if it is going to be a medical industry, we cannot take much risk. So the alpha level alpha will be a 0.01. But it is for manufacturing, then we can talk about 95% confidence. But if you are going to do some test on a medical this thing field, then we will have to be 99% confident. Okay. So after defining the null hypothesis and the alternate hypothesis, and after setting the significance level, then what you do is you collect the data, and then you just go to the software statistical software like Minitab, and then you just key in all the details and then do the appropriate test. So as I told you, there are a lot of hypothesis testings are available, which we are going to discuss shortly, and then we will have to select the right hypothesis test. So what are the different criteria which are used for selecting the right hypothesis test, that also we will discuss. So once you put in the data and then you do that particular test using the Minitab, then the Minitab will give out a p-value, the probability value. Okay. Then depending upon the p-value, if the p-value is lower than alpha, so suppose you have set alpha as 0.05, if p is less than 0.05, then we reject the null hypothesis. If p-value is greater than alpha, then we accept the null hypothesis. So for example, now for that example, whatever we say, we have just put the null hypothesis as mu A is equal to mu B, and for alternate hypothesis mu A is not equal to mu B, and then we have selected alpha as 0.05, and then we have collected the data, input the data into the Minitab software, selected the appropriate hypothesis testing, and then when we did the test, and suppose we get the p-value as 0.52. So since p is 0.52, which is greater than 0.05, so what does it mean? So since if p is greater than alpha, then we keep the null hypothesis. That means we accept null hypothesis. So what does null hypothesis say? That means mu A is equal to mu B. Then what is the conclusion here? Since the mean yield of using A is equal to mean yield using B, that means there is no significant change in the yield because of raw material. So in that case, the raw material is not a root cause for the problem. So that's what we decide. Suppose instead of that, we are getting P is equal to 0.01. So that means it is less than 0.05. If P is less than alpha, then we will have to reject the null hypothesis. So that means you will have to accept the alternate hypothesis. What does the alternate hypothesis say? That mu is not equal to mu B. So in that case, then there is a significant difference in the yield because of change in raw materials. So raw material supplier is one of the key input variable. So in this way, we will be either accepting or rejecting the null hypothesis or alternate hypothesis, and accordingly we will come to the conclusion. So this is how a hypothesis testing is done. So normally a null hypothesis can be accepted or rejected by using the three different methods. So whatever I was discussing was regarding the p-value. If p is less than alpha, then we will reject the null hypothesis. If p is greater than alpha, then we accept the null hypothesis. Then again, we can also do it based on some critical values of the calculated statistics, or we can also do it based on the confidence interval. So again, which type of statistical hypothesis testing you will have to use? will depend upon the so many factors. So what are the factors which will help you to select the appropriate hypothesis testing? So what are the parameters or criteria? What are the criteria based on which the hypothesis testing is selected? One is the data type. So data type, as you know, whether the data is continuous or whether the data is attribute or discrete. Whether the data is continuous or discrete. The second one is whether the data is normal or not normal. So this is again one criteria on which the particular hypothesis testing is selected. Third one is what parameter you want to check. Parameter you want to check. That means whether you want to check the mean or variance or proportion. So depending upon whatever parameter you want to check, the hypothesis testing will be different. Fourth one is the number of data sets. Whether you want to compare, like how here I have compared only two raw material suppliers A and B, but using the hypothesis testing I can simultaneously do even for 5 different suppliers A, B, C, D and E. I can collect the data for 5 different suppliers and then I can do the hypothesis testing. So, but I will have to do a different hypothesis testing. So the number of data sets which is on which I have to do the testing will also determine which hypothesis testing I need to do. So if you really see here, so these are the different types of hypothesis testing which are available. So I will just discuss one by one. So when we are having both x and y as discrete, then we go for if we go for the chi-square test. If both and y are discrete, then we go for chi-square test. If both x and y are continuous, then we go for regression analysis. If y is discrete and x is continuous, then we go for logistic regression. So depending upon the data type, again the type of test whatever you are going to do is different. Then when x is discrete and y is continuous, and then depending upon what we want to check, parameter you want to check, whether you want to check the variance or mean, then if you want to check variance, then you will have to go for the test of equal variance. If you want to check mean, then again you will have to see whether the data is normal or not normal. And if it is normal, then depending upon the number of data sets, if it is going to be a single data set, then we go for one sample t-test. If you are going for two sets of data, then we will go to do two sample t-test. If you want to compare before and after sort of thing, then we go for two sample paired test. If you have two or more, three or more data sets, we go for ANOVA. So like that, these are the 4 criteria on which the test we need to do is decided. One is the data type, then whether it is normal or not normal, and third one which parameter you want to check, and the last one is the number of data sets. Okay. So now, as I told you, since we are not doing the 100% testing, we are only trying to predict based on the samples. So there is always a chance of error in our decision. So sometimes what may happen is we would have accepted null hypothesis, but actually the null hypothesis may not be true. The alternative is also true. That means actually the null hypothesis is not true, but we accepted it. So this type of errors we call it as a alpha error and beta error. So alpha error, it is the probability of rejecting the null hypothesis when it is true. Okay. So typical alpha risk is 5%. Same way, type 2 error or beta error, it is the probability of accepting the null hypothesis when it is actually false. So there is always, since it is the decision is based only on sampling, there is always a chances of error, and the probability of rejecting the null hypothesis when it is actually true, we call that as a alpha error, and the probability of accepting the null hypothesis when it is false, we call that as a beta error. So the beta error is a function of the sample size. So if the sample size increases, the beta error decreases, and 1 minus beta is called the power. So power is the ability of the test to detect a difference if it exists. Okay, this is actually a very very important slide. So this will clearly give you a lot more information. So if you want to really check the normality test, so when I was discussing about how we are going to check the normality, I talked to you about the Anderson-Darling normality test. So this is also a type of a hypothesis testing, and then this is used for data from continuous data points. Then if you want to check the equality of means, and then if we will use the F test if you are having data from two normal groups, Bartlett test if you are having data from more than two normal groups, and Levin's test if we are going to have data from non-normal groups. Same way, if you want to test the equality of means, whether the means are equal or means are significantly different, and when the data is normal, then we can use a two sample t-test or a pair t-test or ANOVA. Same way, we can check for equality of means, but the data is not normal, then we can go for Mann-Whitney, Kruskal values or Morse-Median test, depending upon the number of data points, data sets. Then equality of proportion, either we do a two sample p-test or chi-square t-test. So this table is very very important, which will tell you like this based on the actual conditions, we will be able to select the appropriate test, and then these tests are there in the Minitab. And whenever you collect the samples, you select this particular test in the Minitab, and then you do the testing, then you will get the p-value, and then depending upon the p-value, if it is less than or greater than the alpha value, that is 0.05, if it is, then accordingly you accept or reject the null hypothesis, and accordingly you take the final conclusion. So this is actually the summary of hypothesis testing. So in this session you learnt about the general concepts and goals of hypothesis testing, the significance level, practical versus statistical, alpha and beta risk, and the different types of hypothesis testing.
So in this session, we will learn about doing hypothesis testing with normal data. So by the end of this session, you will be able to do hypothesis testing with normal data. We also will see an example of doing a practical problem in Minitab. We will do a hypothesis testing with normal data using Minitab. In the last session, where we were learning about the hypothesis testing, we learned about the different tests which are available for doing the hypothesis testing using normal data. So whenever we are having a set of data, first thing we'll have to do is we'll have to do a normality test, and then for doing the normality testing, then we use this Anderson-Darling normality test. So the assumption here is the data is from continuous data set. So whenever we are having a continuous data set, so if you want to really check whether the data is normal or not normal, then we'll have to use the Anderson-Darling normality test. So in the Anderson-Darling normality test, the null hypothesis says that H0 says that data is normal, and HA, that is the alternative hypothesis, says that data is not normal. Then you just do the test and find out what is the p-value. So if p is greater than alpha, alpha is normally 0.05. So if p is greater than alpha, then you accept null hypothesis. So that means null hypothesis say that the data is normal. So whenever you are doing the Anderson-Darling test, if you are getting a p-value greater than 0.05, that means the data is normal. If p is less than 0.05, then the data is not normal. So that is how you do the normality test first. And then once you have established the normality test, then the other test, whatever we can do for the normal data, or F test. So F test you will do to check the equality of variance when we are having two sets of normal data. So whenever we are having two sets of normal data and we want to find out the equality of variance, then we use the F test. Then
we will be able to use Barrett's test when we are having data from more than 3 sets of normal data and we want to check equality of variance. So F test and Bartlett test are used to check the equality of variance for normal data sets, and then F test when we have 2 sets of normal data, and Bartlett test we use when you have more than 2 sets of normal data. Then for the equality of means, whenever we have the data sets from normal data points, then we use one sample t-test. If you want to compare whether the particular data set is comparable to a standard mean. So when you want to compare one set of data with a standard mean, then we use the one sample t-test. Then we use a two sample t-test whenever we want to compare data from 2 different continuous normal data sets. So we use 2 sample t-test when we have 2 sets of data and we want to compare whether the means are equal. And then we use the pair t-test whenever we want to check whether there is any logical difference between before and after. Say for example, a doctor is having a set of medicine and then he wants to check whether there is an effect because of taking the particular medicine. So he has the value of that particular health parameter before the medicine was given, and then for the same patient after the medicines are given, so whether there is any change. So we have correlatable data before taking the medicine and after taking the medicine for a particular patient. So like that we can have the data for 10 to 15 patients. Then the pair test will be able to tell whether there is a difference because of using the medicine. So for doing that we use a pair t-test and then we can use it for before and after for 2 sets of normal data. Then analysis of variance we will use when we are having data from more than 2 sets of continuous data where the data is normal, and then we are checking whether the means are equal for more than 2 sets of data. So in summary, we can use Anderson-Darling test for checking the normality of a data. Then for checking the equality of variance, we will use F test and Bartlett test. F test for 2 sets of normal data and Bartlett test for more than 2 sets of normal data. And then for equality of means, we have 4 different tests. The one sample t-test, if you want to compare whether a set of data is meeting the standard requirement. And then 2 sample t-test when we want to compare the means for 2 different sets of data. And pair t-test if you want to see an effect before and after. And ANOVA if you are having more than 2 sets of data. So these are the different tests we can do for the hypothesis testing. So whenever we are doing the hypothesis testing, so there is a step-by-step approach. We cannot directly input the data into a statistical software and then straight away go and do the hypothesis testing. So there is a step-by-step approach. So the first step is the stability study. So whatever the data sets we are having, so first we will have to check whether the process is stable, whether the data has been collected from a process which is stable. So in order to do that, we will have to do the run chart. So whatever the data sets we are having, first we will have to draw the run chart and then see whether the process is stable. So in the run chart, we are looking for any patterns. Then if there is any pattern, so that means the process is not stable. So in that case, we cannot even proceed further in the data collection. We will have to stop the process, try to identify the reasons for the pattern in that particular process, remove that special cause variation in the process, and then rerun the run chart. So only after the stability of the process is established through the run chart, then only we can
carry on with the remaining test. So once we have done the stability study using the run chart and established that, then we move on to the shape study or the normality test. So while doing the normality test, it is not necessary that the data sets has to be normal. So the normality test will tell you what type of tools you are going to use. So if the data sets is going to be a normal, then we can use a particular set of hypothesis testing tools. And if the data is not normal, then we can use a different set of hypothesis test, which you have seen in the previous slide. So doing the normality test will help you to select which tool we are going to use. So for doing the normality test, normally we can plot the histogram and box plot, but we can also do the Anderson-Darling method, Anderson-Darling test, which we explained in the last slide. So after doing the Anderson-Darling test, we will be just knowing whether the data set is normal or not normal. Then once you have completed the normality test, then we can do the equality of variance, whether the equality of variance is there in the data. That means we are doing a spread study. Then again here equality of variance is not a must. So depending upon whether the equality of variance is there or not, then adjustments can be done in the hypothesis testing tool. After you have completed this, the last test will be the centering study. So then using this we will be able to compare whether the means are equal or not. So this can be done by doing a 1 t-test or a 2 t-test or ANOVA. Okay. So the homogeneity of variance can be done by using a F-test or a Bartlett test or F-test and Bartlett test. So the equality of means can be done by 1 sample t-test, then 2 sample t-test, then paired t-test and ANOVA. So now we will just see how this test can be done in the some examples we can see. So suppose one of the practical problem we see is that we are having a set of data and we want to really check whether this data is meeting a target value of 2650. So we have collected the data from the process, 10 data points, and then we want to check whether it is meeting the requirement of a target value of 2650. So this can be done whenever we want to compare a set of data with a standard value, then we go for 1 sample t-test. So here, so we again you just copy the data, then in the Minitab, and then we do the 1 sample t-test. So the output we are getting in this format. So again here we are just checking what is the p-value. So the p-value is 0.770. So that means p is greater than alpha, that is 0.05. So since p is greater than 0.05, that means we fail to reject the null hypothesis. So here the null hypothesis says that mean is equal to 2650 and the alternate hypothesis is mean is not equal to 2650. And since we have failed to reject the null hypothesis, that means we are going to accept null hypothesis. So that means we have to accept that mean is equal to 2650. So the conclusion is that the sample meets the target value of 2650. So that is the inference for this particular data set using the 1 sample t-test. So the inference is that the mean meets the target value of 2650. Okay. So now we will just see how we do a paired t-test.
So here we are having two sets of data. One is the yield before a particular change was made, and the second set of data is the yield after some changes are made. So we want to just check whether change in that process conditions has really helped in improving the yield or not. So we can do the parity for yield before and yield after. So here again the null hypothesis is that yield before is equal to yield after. That means there is no change in the yield. And the alternate hypothesis is yield B not equal to yield A. That means there is a change in yield. So here alpha is equal to 0.05. So once you have defined the null hypothesis and alternate hypothesis, and we have defined the alpha value, then we can just copy the data in Minitab and then do all the studies as we have explained in the first slide. That is, we are going to do the run chart, then the normality test, and then the equality of variance. So after doing all the tests, then we do the parity test in Minitab. So once we do the parity test in Minitab, then this is the output we are getting, and we just see what is the p-value. So p-value is equal to 0.772, which is greater than 0.05. That means since p is greater than 0.05, then we fail to reject the null hypothesis. So that means we have to accept null hypothesis, which that says that yield B is equal to yield A. So that means there is no change in yield because of the process change. So this is the conclusion by doing the parity test. There is no change in the yield because of the process change. So we have compared the data of the yield before and after the process change, and using the data we have conclusively we have proved that change in the process condition has not made any impact on the yield. So since p is greater than 0.05, no enough evidence failed to reject the null hypothesis. Okay. Now let us try to do a F test. So this F test we are doing in order to check whether the variances are equal. So the problem here is a new filtering device is installed in a chemical unit. Before its installation, a random sample yielded the following information about the percentage of impurity. Y bar is equal to 12.5, S1 square, that is the variance square, is equal to 101.17, and N1, that is the sample size, is 8. So after installation, again a random sample yielded Y2 bar is equal to 10.2, variance is equal to 94.73, and the sample size is equal to 9. So can we conclude that the two variances are equal? So as explained before, again whenever if you want to check whether the variances are equal, and we have two sets of data, and we have also done the normality test, and then we have proved that both the sets of data are normal, then we can go for F test. So again what you do is you just input the data in Minitab, and then we just see what is the output we are getting. So the output from the Minitab is like this. So again we find that the after doing the F test, we find that the p-value is 0.912. That means greater than 0.05, that is the alpha. So that means the variances are equal. So again we can just see the interval plot, and then we can find that there is no significant difference in the variances of sample 1 and sample 2. So using the F test, we can conclusively prove that the variances of the sample before and the sample after
are same. There is no difference in the variances of these two samples. Next we will just see how we can do a two sample t-test and see whether there is a significant change in the average values of the yield. So again we will just use the same data. That is, a new filtering device is installed in a chemical unit. Before its installation, a random sample yielded the following information about the percentage of impurity. Y1 was equal to 12.5, S1 square is equal to 101.17 and N is equal to 8. After installation, a random sample yielded Y2 bar is equal to 10.2, S2 square is equal to, that is the variance is 94.73 and number of samples equal to 9. So has this filtering device reduced the percentage of impurity significantly? So now we have the data that the impurity percentage was 12.5 before the filtering device was installed, and again the Y2 bar is equal to 10.2. That means the average impurity is 10.2 after the filtering device has been installed. Now we want to check whether there is a significant reduction in the impurity level because of putting the filtering device. So now again we do the test in the Minitab. We copy the data in the Minitab and then the check for the p-value in the Minitab. So we find that the p-value is 0.947. So since p is greater than 0.05, no significant difference in the mean impurities. So here again the null hypothesis is mu before is equal to mu after, and alternate hypothesis mu before is not equal to mu after. And since p is greater than 0.05, then we cannot reject null hypothesis. So null hypothesis is accepted. We fail to reject the null hypothesis. So that means we reject alternate hypothesis. So that means the null hypothesis holds good. That means the impurity before and after there is no significant change. So the conclusion is that there is no significant difference in the mean impurities. So that means the installation of filtering device has not significantly reduced the impurity level. Okay. Now we will just try to do a ANOVA test. So we have seen from the previous slide that ANOVA test is used for comparing the equality of means for more than two sets of normal data. So now the problem here is we are having 3 brands of batteries are under study. It is suspected that the lives in weeks of the 3 brands are different. So 5 batteries of each brand are tested with the following results. Are the lives of the 3 batteries different? So we want to now check whether the brand type, brand 1, brand 2, brand 3. So whether brand type is having the impact on the life of the battery. So here the null hypothesis says that B1 is equal to B2 is equal to B3. That means the lives of all the 3 brands are equal. And then the alternate hypothesis says that at least one brand is different. So now using the data we have to see whether the null hypothesis is true or the alternate hypothesis is true. Then again we just input the data in Minitab, and this is what we are getting the output from Minitab. So we are checking the p-value. So since p is less than 0.05, so that means we reject the alternate hypothesis. So alternate hypothesis, since p is less than 0.05, so that means we accept alternate hypothesis. So alternate hypothesis is true. So that means at least one brand, the mean battery life is different. That means the type of brand is having impact on battery life. So that means battery type is having an impact on the life of the battery. And then what we can see is that since we are getting a R square value of 84.2, so that means this battery type is accounting for 85% of the variance. So about this we will learn more whenever we are learning about the regression, about the R square values, how it is very significant. We can learn more whenever we are learning about the regressions. So here doing the ANOVA test, we are just proving that since P is less than 0.05, that means at least one battery type is having a different life. That means battery type is having the impact on the life of the batteries. So we will have to reject the null hypothesis. So at least one department is one battery type is different. So again, if you see the box plot of the different three different battery types, so brand 1, brand 2 and brand 3. So you can find that brand 2, the mean value is somewhere around 80 weeks, whereas for brand 2 and brand 1 and brand 3, it is somewhere between 95 to 100. So the life of brand 2 is different when compared to the life of brand 1 and brand 3. Okay, now we have seen how the different tests are being done in Minitab. We have done one sample t test for checking whether the mean is equal to a standard. Then we have done a F test to check whether the variances are equal. Then we have done a pair t test to check whether the difference in the process was having an impact on the yield before and yield after. Then we also did a 2 sample t test to check whether the means were equal, and then we also did the ANOVA test to check whether the life of the batteries was depending upon the battery type. So now we will just do a demonstration in Minitab. So we will do a 2 sample t test in Minitab. So first what we do is, again we will just try to understand what is the problem and then see how this practical problem can be solved by using the hypothesis testing, and then we will just demonstrate that in Minitab. So we have the practical problem, then this practical problem we will convert that into a statistical problem by writing a appropriate hypothesis testing. Then we will solve this problem statistically in Minitab by using statistics, and then we will get the statistical solution. And then once we have the statistical solution, and then see how this can be converted into a practical solution, and then how the process problem can be solved. So now the practical problem is here a manufacturer is using 2 different catalyst type, and then catalyst 1 and catalyst 2, and currently the catalyst 1 is in use, but catalyst 2 is also acceptable. But now there is a suspicion that because of the change in catalyst 2, there may be a change in the yield. So if there is going to be a reduction in yield because of using the catalyst type 2, then switching over to catalyst 2 will not be advisable, because then the reduction in the yield will have an impact on the overall costing. So now before switching to catalyst 2, you will have to really statistically establish whether there is a difference in yield because of changing from catalyst 1 to catalyst 2. So for which again we have done some 8 sample pilot tests using catalyst 1 and catalyst 2, and the data are given. So now using the data, then we will have to really see whether the yield is affected by the change in the catalyst type. So now we will use Minitab to find a solution for this problem. So now what we do is we just copy paste the data in Minitab, and then we will continue the test in Minitab. Now I have copied the data for Catalyst 1 and Catalyst 2 in Minitab. Now let us follow the step-by-step approach as we have seen in the beginning of the session. So first we will start with the run chart to check whether the process is stable while we are collecting the data from process 1 and process 2, that is using Catalyst 1 and Catalyst 2. So first we will start with the run chart to check for the stability test. So just go to Stat, Quality Tools, Run Chart. So first I start with Catalyst 1, subgroup size is 1, then I click OK. Then I get the run chart for Catalyst 1. So here you see that the individual readings for the 8 batches are randomly distributed above and below the mean. So there is no visible patterns are there. So that means the process is running under the influence of only the common cause variation, and the process is stable since there are no patterns. Okay, so the process when is running in using Catalyst 1 is stable. That is what is the conclusion by the run chart. Then we do the same test for Catalyst 2. So again go to Stat, Quality Tools, Run Chart, and I am collecting the copying the data for Catalyst 2 and doing the test for Catalyst 2. So when I press OK, then this is what the run chart I am getting. Again for run chart, again you are finding that the data are randomly distributed below and above the mean. So there is no visible trend. So that means the process is stable and running under the only the influence of common cause variation. So now we have seen that the process when it was running using Catalyst 1 and Catalyst 2, both the time the process were stable. So we can now proceed for the next study, that is the shape study. So shape study means we will have to check whether the data is normal. So in order to do the normality check, again we go to Stat, Basic Statistics, Normality Test. So first I do it for Catalyst 1 and then click OK. So this actually is the result of the normality check using the Anderson-Darling method, and here again the hypothesis testing is that the null hypothesis says that the data is normal, and the alternate hypothesis says that the data is not normal. Then we have to calculate the p-value. So since the p is greater than alpha, that is 0.05, so that means we will have to we don't have any evidence for rejecting the null hypothesis. So that means we are accepting the null hypothesis. We say that the data is normal. So Catalyst 1, that means it is having the normal data. Then similar test we do for Catalyst 2. Again Basic Statistics, Normality Test, and then I select Catalyst 2. Then click OK. Then I calculate the p-value. So p is again greater than 0.05. That means the data is normal. So now we have done the normality test for both the sets of data using Catalyst 1 and Catalyst 2 and found that the data is normal. Then we next move to the next step, that is we will have to check the equality of variance. So again for that again we go to Stat, Basic Statistics, and to variance. So here the samples are in different columns, and the first sample is in Catalyst 1 and second sample is Catalyst 2. And then graphs, I can just say I will just go for interval plot and then I will go for box plot to really check how the variance is there. Then I click OK, click OK. So here again these are the results of doing the F test. So F test is done to check the equality of variance when we have data from two sets of normal data, and here the p-value is 0.569. So that means again the null hypothesis says that the data are having equal variance, and the alternate hypothesis says that the data are not having equal variance. Since p-value is more than 0.05, so that means the null hypothesis we don't have any evidence for rejecting, so we accept the null hypothesis. That means we prove that the data are having equal variance. So this can be again substantiated by seeing the interval plots and the box plot. So we are finding here that the median is almost same, the variance is also not much difference is there. Same way, if you see the interval plot also, not much difference is there. So that means again the equal variances can be assumed whenever we are checking for the equality of means. So now we have done the check for stability. That means we have run the run chart for both catalyst 1 and catalyst 2 and found that the process was stable in both the cases. Then we did the normality check for both catalyst 1 and catalyst 2, and we found that both the data were having normal distribution. Since both the sets were having the normal data, then we use the F test for doing the equal variance test, and then when we did the equal variance test using F test, then again we found that the p-value was more than 0.05. That means the data is having equal variance. Now we proceed to the last stage, that is the checking the equality of means. So again from the table whatever you have learned, so if the data is having normal data, two sets of data, and where the equality of variance can be assumed, then we can go for the two sample t-test. So now we do the two sample t-test for checking whether the mean yield is same or there is a difference in mean yield. So here the hypothesis testing is H0 is means are equal for catalyst 1 and catalyst 2, and the alternate hypothesis is that means are not equal. Then I go there to the Minitab and then check stat basic statistics two sample t-test. The samples are in different columns. First sample is in catalyst 1, second sample is in catalyst 2, and I have already done the F test from where we can do the assume the equal variances. Then you can also see the box plots to check how the variances are there. Then I click OK. So here this is the output of the two sample t-test. So here you find the p-value to be 0.729. So since p is greater than 0.729, we do not have any evidence for rejecting the null hypothesis. That means we are accepting the null hypothesis. So the null hypothesis says that the mean yield of catalyst 1 is equal to the mean yield of the catalyst 2. So that means there is no difference in the mean yield while using catalyst A and catalyst B. So now the conclusion is that the catalyst type does not have any impact on the yield. So now we go back to the practical problem. So the practical problem was we wanted to check whether there is a difference in yield because of changing over from catalyst 1 to catalyst 2. So now we have statistically proved that there is no change in the yield because of changing to catalyst 2. So now since catalyst 2 is cheaper, now the process specialist can recommend for switching over to catalyst 2. Since we have statistically proved that there is no change in yield because of using catalyst 2 and the catalyst 2 is cheaper, then the company can change over to catalyst 2. So we had the practical problem to see whether changing to catalyst 2 was having an impact on yield. Then that was converted into a statistical problem. Then we just did a hypothesis testing, and then there was a statistical solution from the hypothesis testing saying that there is no change in the mean yield, and then we converted the statistical solution into a practical solution, and then the process specialist can recommend for changing over to catalyst 2. So this is how we solve the process problems using the statistical tools through Minitab. So this way hypothesis testing will be able to clearly identify whether there is a difference whether there is a difference in the means, and then from that we will be able to come to some conclusion. So in this session we have learnt about hypothesis testing with normal data. So we understood how the hypothesis can be done using, say, if we saw how one sample t-test can be done, how the f-test can be done to check the equality of variance, then how the paired t-test can be done to check whether there is a difference because of changing the process condition. Then we also saw two sample t-test, how it can be used to see whether the means were equal or not. Then we also saw how ANOVA test can be used for checking whether there was the equality of mean for more than two sets of data. We also saw how the hypothesis testing can be done in Minitab for normal data. So we have learned about hypothesis testing with normal data in this session. So in this module we will learn about the hypothesis testing with non-normal data. So by the end of the session you will be able to do hypothesis testing with non-normal data. So the hypothesis testing with non-normal data, we also call that as a non-parametric testing. Non-parametric. So the difference between parametric and non-parametric is, parametric means there is a pattern. So either it is, we can call that as either a normal distribution or binomial, or it is following a specific pattern. That's why we call that as a parametric thing. But whenever we do not have any pattern, a distribution does not have any pattern, we call that as a non-parametric. So whenever we are testing some data which does not have any pattern or any probability distribution, then we'll have to use the non-parametric test. So here are the cases when we'll have to use the non-parametric test. The first one is when data are obviously non-normal. So we'll have to use the non-parametric test whenever the data are not normal. So how do you find whether the data is normal or not normal? That means you do the normality testing by do the normality test. What is the name of the normality test? That's the Anderson-Darling normality test. So you do the test and see what is the p-value. If p is greater than 0.05, that means data is normal. If p is less than 0.05, then this is not normal. So if the data set is not normal, then you go for non-parametric test. Okay. So we use the non-parametric test when the data are not
normal. Then we also use a non-parametric test when the sample is too small for the central limit theorem to lead to normality of averages. So at the time of discussing the central limit theorem or CLT, we found that if the sample size is more than 30, then if you take the averages of the individual readings, then maybe the data set can be converted into normal data. But in some cases, if we are getting only few samples and then we will have to take a decision based only on few samples, which is less than 30, then again we cannot use any hypothesis test based on normal distribution. Then we will have to go only for the non-parametric test. And third one, when the distribution is not at all known. When we know that we do not have any idea about what is the distribution that particular data is following, then we will have to use non-parametric tests. So non-parametric tests are used when the data are obviously not normal, when the sample size is too small, or when the distribution is not known. The third one is when last one is when the data are nominal or ordinal scale. But whenever you are doing the non-parametric test, you will have to know that again we are having some assumptions, right? So the non-parametric tests, they do not make assumption about the population distribution. They do not follow a specific probability distribution. But the only assumption is that the samples are coming from any identical continuous distributions or symmetrical populations. Okay. First we will have a look at the Wilcoxon signed rank test. So the example we are seeing here is a test is conducted where customers are asked to rate two products based on various criteria and come up with a score between 0 and 100 for each. The tester's goal is to check whether product A, the new version, is perceived to be superior to product B. The null hypothesis would be that they are equal to each other. So what you are now trying to do is there are two products, product A and product B. So product A is the new version and product B is the old version. And then we are just getting the ratings from different customers. So rating from the different customers. So since the ratings are given by the customers, and then this is not a continuous data, and then it is only a ranking data with the ordinal data. So we are having the data maybe in the next slide we are having the data points. So this is the data for product A, 55. In the rate of 1 to 100, they are given 55, 60, 77, etc. For product B, 50, 62, 70, 78, etc. So we are having the ratings from the different people for both the products. So the measures are rankings by people, so the data are not necessarily interval scale. So we cannot say that there is a proper interval between these readings, and they are also not certainly that ratio scale. So that's why we cannot use a paired sample t-test since the data is not normal, and a non-parametric equivalent of that is the Wilcoxon signed rank test. So if the data is normal, then we would have done a paired t-test, but since the data is not normal, then the equivalent test for the non-parametric test is the Wilcoxon signed rank test. So this is similar to the signed test but more sensitive. So that's why we have selected this Wilcoxon signed rank test. So again we find the null hypothesis is that both the product A and product B are same, and alternate hypothesis is that there is a difference between product A and product B. So the Wilcoxon signed rank test uses the magnitude of the differences, rank orders them, and then applies the sign of the difference and computes the sum of those ranks. So the assumptions are data are at least ordinal in nature, the pairs are independent of each other, and dependent variable is continuous in nature. So whenever we are again inputting the data in Minitab, then the results whatever we are getting is like this. So here you see we have 10 number of data points, and then for these 10 number of data points, the Wilkins set is 44 point, and the p-value is 0.046. So that means p is less than 0.05. So which means there is a difference. Okay, there is a difference between A and B. So using the non-parametric test, that is the Wilcoxon test, since we are finding that the p is less than 0.05, so that means there is a difference between the products A and B. Okay, next we take an example of a two-proportion test. So here again we want to compare two processes. The process 1, in process 1 we have rejected 31 applications out of 3,450 applications in 1 year time, and in process 2 34 applications were rejected out of 2,364 during the same time interval. So we want to check whether there is a difference in process 1 and 2 or there is no difference. So again, as usual, the null hypothesis is always equal. That means P1 is equal to P2. That means both are same rejections. And alternate hypothesis is they are not same. Rejections are not same. That is P1 is not equal to P2. Then input the data, select the two-person proportion t-test, and find out what is the p-value. So the p-value or the probability value is 0.065, which is greater than 0.05. So that means accept as 0. So that means both processes have same failures. Then chi-square test. So chi-square test, I had already explained to you, is used to test whether there is a relationship between two sets of data. So the null hypothesis here is that there is no relationship between the variables, and the alternate hypothesis is that there is a relationship between the two variables. So now let us take an example. Let's say that we wanted to determine if there is a relationship between races and smoking. So we want to see whether there is a relationship between the race of the people and their smoking behavior. When we test if there is a relationship between these two variables, we are trying to determine it being a part of a particular race makes an individual more likely to be a smoker. So that means if a particular person is belonging to a particular race, is there any possibility that he is most likely to become a smoker? So in that case, we can say that race and smoking are related or associated. So we want to establish here, or we want to check whether race and smoking behavior are related or not related. So again, we have the data here. So we have done a sort of a survey, and we found that Caucasian, the race, the number of non-smokers are 620 and the number of smokers are 75. Same way for black, it is 240 and 41. Hispanic 130 and 29, and for others it is 190 and 38. So this type of table in which you are collecting the data, we also call this as a contingency table. So by considering the number, if observation falling into each category, we will see how to test the hypothesis and the form. So H0, the two variables are not associated, and HA is the two variables are associated. Then again, we just input the data in Minitab and then select the chi-square test, since we are checking for the association or the relationship between these two variables, and then we get the p-value. So p-value here is 0.023, which is less than 0.05. So that means alternate hypothesis is accepted. So alternate hypothesis is accepted, which means the two variables are associated. So that means there is a relationship between the race and the smoking behavior. So we have seen both the examples of hypothesis testing with the normal data as well as with the non-parametric testing. So in both the type of testing, we find that the general procedure we are following is we are specifying what is the null hypothesis, we are specifying what is the alternate hypothesis, we are setting the alpha level, and then we just select the appropriate hypothesis testing, and then we collect the data, and then we input the data into the Minitab software and select the appropriate tool, and then we just run the tool, statistical tool. So the tool will give the output, and in that output you check for the p-value, probability value. So if the p-value is greater than 0.05, then accept the null hypothesis. If p is less than 0.05, then you reject the null hypothesis. So that is why, if you remember, in the define phase, whenever we are talking about y is equal to f of x thinking, then I was describing you how a problem is getting analyzed in the Six Sigma methodology. So what normally happens is we first start with a practical problem. So the practical problem in these cases is whether there is a relationship or not, whether the mean is, the yield is related to the supplier or not. So like this we are trying to see whether whether x is having an impact on y or not. So that is a practical problem. So this practical problem we are converting into a statistical problem. So a statistical problem means what? We are just building the null hypothesis and alternate hypothesis. So we are just using the hypothesis testing and framing the null hypothesis and the alternate hypothesis, so that we are converting the practical problem into a statistical problem. And then once it is converted into a statistical problem, then we collect the data, and then from the data and calculating the p-values, we are getting the statistical solution. So we are getting the statistical solution, so depending upon p-value. So that means whether less than alpha value or greater than alpha. So depending upon the p-value, we come to a statistical solution, whether null hypothesis is accepted or alternate hypothesis is accepted. So once we find the statistical solution, then we convert that into a practical solution. Then based on this p-value, we decide whether the means are equal or variances are equal or not, or whether there is an association or not, whether there is an improvement or not. Accordingly, we are taking the practical solution. So this is how we normally validate the root causes in the analyze phase using the hypothesis testing. So in this session, we have learnt about the hypothesis testing with non-normal data.